let's go for it. So it is my pleasure to introduce you to Yi-Lin from the, correct me if I'm wrong, from the New York University.
Yes.
Even though in the past she has done very interesting work, also in infant physical reasoning with René Deyajon at University of Illinois at Urbana-Champaign. Among her research interests, she works on language acquisition and infant cognition research. And before this research phase, she was also making a bachelor's on psychology and economics at the Smith College and a Master of Science on psycholinguistics at the University of Edinburgh. So being that said, thank you so much to be here today, Yi-Lin. And I let you share your screen.
Thank you so much. That's a very kind introduction. Thank you so much for having me and coming to this talk. So before I start, I actually need to thank lots of people, many of whom their work is going to be cited heavily in this talk. And in particular, I need to thank my PhD advisor and collaborator, Renee, who is here with us today, as well as her colleagues and students, many of whom work spent many years studying infants' representations of the world and objects in physical events is just one of them. Okay, so with that being said, let's start. So decades of research on how infants represent objects in physical events has yielded 3 sets of rather puzzling findings. First, infants can often successfully reason about broad categorical information about objects, but they often fail to detect violations that involve fine-grained featural information. For example, infants as young as 2 to 4 months can detect a violation shown in the upper row, where a toy mouse disappears behind one screen and reappears from behind the other screen without appearing in the gap between them. Similarly, in the bottom row, infants also detect a violation if a cover is lowered over a toy duck, slid to the side, and then lifted to reveal no duck at all. In both cases, very young infants can reason about very broad information, such as whether an object should be able to pop in and out of existence. Here is another example. 6-month-olds detect a violation if after seeing a ball placed behind a screen, they then see the screen removed to reveal a human doll head behind it. In this case, young infants can use the categorical distinction between human-like and non-human to detect the impossible change. Along these successes, however, infants fail to detect many other core violations that can only be detected by attending to fine-grained information about the sizes, shapes, patterns, and colors of objects, or about the details of their spatial arrangements. For example, also at 6 months, infants fail to detect violation if a tall object is lowered into a short container until it becomes almost fully hidden. They also fail to detect a violation if a dotted ball changes into a striped ball when passing behind a screen that is too narrow to hide more than one ball. Even at 12 months, infants don't find it unexpected if a purple toy changes into an orange toy when lowered into a container that is too small to hide more than one toy. And as shown in the bottom row, infants don't find it unexpected if an asymmetrical object remains stable when released with only its smaller end resting on the base. So why is that infants succeed with broad categorical information but fail with featural information? This is the first set of puzzling findings. When infants start to successfully reason about particular featural information and tasks, they often succeed with events from one category, while they fail with events from another category. I'll illustrate this point with the feature of height. By 3.5 months, most infants detect a violation when they see a tall cylinder become almost fully hidden when lowered behind a short container. However, it's not until about 7.5 months that infants detect a violation if a tall object becomes almost fully hidden when lowered inside a short container. Moreover, it is not until about 12 months that infants detect a violation if a short cover is lowered over a tall object until this object becomes fully hidden. And it's not until about 14 months that infants detect a violation if a tall object becomes fully hidden when lowered inside a short tube. And we see the same patterns with other features, such as color and pattern. So why do we see these developmental lags in infants' ability to reason about particular features? This is puzzle set number 2. When infants can reason about particular features in tasks that involve change or interaction violations, like the ones that we just seen, they often fail with individuation violations. To illustrate this difference between the two types of violations, let's first consider an event that we've seen so far. It's very similar, in which a big yellow duck goes behind the screen, and the screen lowers to reveal a duck that is small, green, and dotted. The screen is too narrow to hide more than one toy. By 12 months, infants can use many types of featural information, like size and pattern, to detect this impossible violation. Yet, if we change the event slightly, such that a big yellow duck emerges on one side of the screen, then returns behind it, and a small green dotted duck comes out from the other side and goes behind it. Infants at 12 months do not detect a violation when the screen lowers to reveal only one small green dotted duck. So why is it that infants can use featural information to detect change in interaction violations, but not violations in object individuation? That's puzzle number 3. These 3 sets of puzzling findings have made it quite challenging for infant researchers in our quest to come up with a single coherent model of how infants represent objects and physical events. Today, I would like to describe a two-system model of infants' physical reasoning that tries to reconcile these seemingly contradictory findings and to make new predictions. So in the rest of the talk, I'll describe the model, its key assumptions, how this model can account for all 3 sets of puzzling findings, as well as generating novel predictions that we then test. All right, so let's start with the architecture of the model. When infants watch objects interact in a physical event, at least 2 systems are involved in the representation of the event. The object file system builds a temporary representation or a file for each object, and its main role is to identify and track the objects. The physical reasoning system, on the other hand, builds a representation of the causal interaction between objects to predict how this interaction will unfold. Let's imagine a young infant sees this static scene. It might seem familiar from before. A toy mouse stands to the left of 2 screens placed a short distance apart. As infants look at the scene, the OS system builds a temporary file for each object, drawing on incoming perception and stored knowledge. The file for each object includes 2 types of information: identity or what information, and spatial temporal or where and when information. Each type of information includes broad categorical descriptors as well as more fine-grained features. Now imagine that the objects in our scene become involved in causal interaction. The mouse moves behind the first of the 2 screens and becomes hidden from view. At this point, the PR system also becomes engaged and builds a specialized representation of its interaction to predict how it will unfold. In the first few months of life, the PR system's representation of the objects in this event will tend to be very sparse, because this system represents information that the object file system passes on to it at the beginning of the event. And early on, the object file system passes on only categorical information. So even though the information is going to be sparse, there's still sufficient to allow the infants to detect many physical violations, because innate core principles and concepts guide the PR system's interpretation of the information that it does represent. These core principles include persistence with its many corollaries, and the principles of gravity and inertia. And the core concepts include force and internal energy, which makes possible, for example, self-propulsion. And of course, these core principles and concepts that we study in infants are only rudimentary versions of those used by physicists. This initial sparse representation is why very young infants can reason about broad categorical information like that an object should continue to exist as it travels behind two screens with a gap in between them, and that an object should not spontaneously change from a non-human object into a human-like object. And yet they fail when reasoning about fine-grained feature information like color and pattern. These information are not represented by the PR system initially, and therefore infants cannot detect violations that involve these features. And this is the pattern that we saw with puzzling set number 1. And of course, over time, infants' representations become more detailed, and there is a lot of learning that takes place. And this learning process has a few key characteristics. First, beginning at an early age, infants form event categories. And by event categories, we mean causal interactions between objects. Each object in the interaction is assigned a specific role. These early categories include occlusion, containment, covering, tube, support, and collision. Second, for each event category, infants acquire rules that identify causally relevant features for predicting outcomes. The rules are stated in terms of event roles, and the features identified are typically properties of objects, their arrangements, weather displacements. To give you an example of a rule, as we've seen by about 3.5 months, most infants have acquired a rule that identifies height as a causally relevant feature in occlusion events. When an occludee is behind an occluder, their relative heights will determine whether the occludee will be fully or only partly hidden. After infants acquire this rule, they expect a tall occludee to protrude above a short occluder. So they detect the violation shown here. As the toy carrot passes behind the screen, they expect it to appear in the window as it is taller than the window's lower edge, and they detect a violation if it does not. So how are infants able to detect this violation? In our model, as the PR system forms event categories and acquires rules, its interactions with object file system changes in the following way. When an event starts, the PR system now uses the categorical descriptors supplied by the object file system to categorize the event and to assign appropriate event roles to the object. Next, the PR system accesses the list of features it has identified as causally relevant for this event category, and it then taps the OS system for information about these features and only those features. That information is then added to the PR system's representation of the event. And finally, this representation is interpreted by the PR system's domain knowledge, which includes both core knowledge and acquired rules to predict how the event will unfold. So if we go back to our toy carrot event here, the idea is that the PR system will first categorize the event as an occlusion event, with the screen as the occluder and the carrot as the occludee. Next, it will access the list of features it has identified as relevant for this particular category. At 3.5 months old, this list will include height. And so PR system will tap the OS system for information about the relative heights of the two objects. Finally, the PR system will use this information together with its domain knowledge to predict that the carrot will appear in the screen's window, and it will flag the event as a persistence violation if the carrot does not appear as predicted. A third characteristic of this learning process is that once a feature has been identified as causally relevant for an event category, information about this feature will become routinely included when representing any event from the category. This leads to powerful generalizations in at least 2 ways. First, infants who can detect a core violation involving a feature in one event category will also be able to detect the same violation in other events from the category, irrespective of how perceptually dissimilar these events might look. And second, infants will also be able to detect other violations involving the feature in events from the same category. Now let's unpack these 2 points. So we saw a moment ago that 3.5-month-olds can detect a violation shown in the first row. At about the same age, they also detect a violation when a tall object is lowered behind a short occluder until it becomes almost fully hidden. And when infants begin to reach for objects, they also show sensitivity to height as an occlusion feature in their actions. After being introduced to a tall frog, 6-month-olds are more likely to reach for it behind a tall as opposed to a short occluder, suggesting that they do realize only the tall occluder could hide the tall frog. And importantly, notice that all these events are perceptually very dissimilar, and nevertheless, they all involve reasoning about whether an occludee should protrude above its occluder. And infants who have identified height as an occlusion feature can reason successfully about all of these. Now turning to the second form of generalization, infants who have identified height as an occlusion feature can apply it to different facets of occlusion events. So they can use it to reason not only about whether an occludee should protrude above its occluder, as we just saw, but also about whether an occludee should still have its original height when it comes out from behind its occluder. So as shown here, young infants detect a change violation when a tall object that is moved behind a container is much shorter when it's brought back into view. And similarly, older infants detect a violation when a cover is slid in front of a short object and then slid back to reveal a much taller object. Now, in sharp contrast to the powerful generalization that we observed within event categories, there is no generalization across event categories. Infants learn separately about each event category, so that a feature that is identified in one category is not generalized to other categories, even when they might be equally relevant. And a consequence of this lack of generalization or transfer is that when several months happen to separate the identification of the same feature in different categories, this results in striking discrepancies or lags in infants' responses to events from these categories. And that might sound familiar because that's the second set of puzzling events findings that we saw. That there's a 4-month lag between when infants detect violations with height and occlusion events and with height and containment events. Yet more months pass before infants can detect violations with height and covering and tube events. Now, one important assumption of our model regarding the learning that takes place is that infants learn what to include in the PR system's representation about the object, but not how to reason about the information. Innate core principles and core concepts will allow the PR system to interpret any information that is included in its representation. So this assumption brings us to our first novel prediction. If we can prime the OS system to pass on to the PR system features, and crucially features that the PR system has not yet identified to be causally relevant for a given event category, then the PR system should be able to interpret this information using core knowledge. We tested this prediction in a series of priming experiments in a recent paper. I'll illustrate the priming of proportional distribution. So by 13 months of age, but not before, infants identify the rule that a supportee is stable when released with one end on support if the proportion of the supportee that rests on the support is greater than that of the support. Quite a mouthful. We tested whether we can prime 11-month-olds to reason successfully about proportional distribution, even though they have not yet spontaneously identified this feature as causally relevant for support events. So in this experiment, we first showed infants 2 priming trials. In each trial, infants saw an array of 4 L-shaped boxes that varied in height. And the idea is that seeing these arrays induces the OS system to include the relative proportions of the 2 ends of the boxes and to pass on the information to the PR system. And once included, the PR system would be able to reason about it. And importantly, note that infants do not see any support events that will allow them to learn about proportional distribution. After the priming trials, we showed infants an event in which a tall L-shaped box is placed on the base, with the smaller end on and the larger end off. And when the hand releases the box, it remains stable. 11-month-olds who typically do not detect this violation now succeeded. In a control group, we showed infants 4 boxes are equal in height, and these infants did not succeed in detecting the violation at test. So infants succeeded only when they were primed to include proportional distribution in their representations about the object. So our first prediction about being able to prime features bore out. The PR system can reason about the feature information that it has about an object, irrespective of how that information came to be included. This finding confirms that the PR system learns what information it should include and not how. This priming effect is very unlikely, however, to lead to long-term learning. That is, the PR system is unlikely to start now routinely include proportional distribution information when reasoning about support events. It hasn't acquired a rule for it. And so how do infants identify new rules and come to routinely include features in their representations? One of the key learning mechanisms in our model that enables infants to do this is explanation-based learning, or EBL for short. EBL consists of 3 main steps. First, encountering events with contrastive outcomes that infants cannot explain or trigger the process. Second, infants look for a feature whose value maps onto the contrastive outcomes. For example, one value of the feature leads to one outcome, and another value leads to another outcome. If they can find such a feature, they try to build a plausible explanation for it using their domain knowledge. And if they succeed, they generalize this explanation into a candidate rule. And at the last step, this rule is evaluated against a few further exemplars that will either confirm or reject the rule. If this description of the EBL is correct, then another prediction is that one should be able to teach infants features they have not yet identified by showing them observations that trigger and support EBL. And this was tested in a recent experiment, a series of experiments in which Renee and Jerry DeJong, I hope I said his name correctly, they attempted to teach 11-month-olds the feature proportional distribution in support events. As we saw before, this feature is not identified until infants are about 13 months of age. So in this experiment, 11-month-olds received 3 pairs of teaching trials. So 6 trials altogether. As shown here, each pair involved an asymmetrical box. The box varied in size, shape, color, and pattern across the pairs. Each teaching pair included a small on and a large on event. At the start of the small on event, an experimenter hand placed the smaller part of the box on the base, leaving the large half unsupported. When the hand let go, the object fell. In the large on event, the larger part of the object is placed on the base, leaving the smaller half unsupported. When the hand let go, the object remains stable. These teaching events were specifically designed to trigger and support EBL. So let's walk through these steps. First, when the object was placed on the base, the object sometimes fell and sometimes remained stable. Infants were thus confronted with unexplained variation in the outcome, which should trigger learning, because it signaled to the infants that something was missing from the representations of the events. Something needed to be added in order to better predict the event's outcome. Second, the events made it easy for infants to identify the proportion of the entire object that is supported as a potentially relevant feature. When the larger half was on the base, the object remained stable. When the smaller end was on the base, the object fell. Infants could then generate a plausible explanation for this feature using their domain knowledge. In particular, the base could not block the box's fall when less than half of the entire box is on top of the base. The box simply does not have adequate support. Infants could then generalize this explanation into a candidate rule When an object is released with one end resting on base, the object will remain stable as long as the proportion of the entire object that is on the base is greater than that of the base. Finally, if infants were able to generate this rule in the first pair of teaching trials, they could then use the second and third pairs to confirm the rule. And as predicted, 11-month-olds did identify proportional distribution as a support feature when shown these teaching trials. After the teaching trials, they detected a violation when shown new events in which another asymmetrical box remains stable when the smaller end of the box is on the base, but the larger end was off. In additional experiments, they show that disrupting each step in the EBL process led to failures. Infants will no longer identify proportional distribution as a support feature. As an example, one experiment disrupted the explanation step. The boxes remained stable when the smaller end was on the base and failed when the larger end was on. This time, infants no longer succeeded in identifying proportional distribution as a feature because they could not build a plausible explanation for the outcome of these events. So thus far, we have seen that the different roles of these two systems and the interactions explain the first two sets of puzzling findings. And now we'll continue on to the last kind of interaction between the two systems. When the event comes to an end, the two systems must jointly decide how many objects are present in the event so that they can continue to track these objects into the next event. The two systems, however, use slightly different information to individuate the number of objects. The object file system uses mainly categorical information, while the PR system uses both categorical and featural information. Because the two systems use slightly different information, they will sometimes agree and sometimes disagree. Let me illustrate how this works. So first, imagine that infants see an event in which a big yellow duck emerges from one side of the screen, goes back behind, and another big yellow duck that looks identical emerges from the other side of the screen and goes behind. At the end of the event, the OF system thinks there is one object that is closed, non-human, and inert. The PR system thinks there is one object that is closed, non-human, inert, but it's also big and yellow. Even though they use slightly different information to represent the objects, both systems will agree in this case that there is only one object. And so all is well. They predict one, and when they see one, that is perfectly fine. Now let's go to this event that we've seen before. The second object that comes out from behind the screen is instead small, green, and dotted. And the screen lowers to reveal only one duck. This time, the object file system still thinks there is one closed, non-human, and inert object. The PR system, however, thinks there are two different objects based on also size and pattern. So these two systems will disagree on the number of objects that are present. When they disagree, our model predicts that there will be a catastrophic individuation failure. And that means infants will have absolutely no expectations about how many objects there will be when the screen is lowered. We tested this prediction recently. So after seeing two different cups emerge in alternation from either side of the screen that vary in pattern, 11-month-old infants did not detect a violation when the screen was lowered to reveal nothing behind the screen. When they have no expectations, nothing is as good as one or two things. The third kind of interaction between the object file and PR system at the end of the event can account for why even when infants can reason about particular features in change and interaction violations, they still fail to detect individuation violations. And that's the third set of puzzling findings that we saw before. Our model also makes several other novel predictions about this step. I won't go into these at all, actually. So I've put two more predictions here because of time. I'll be more than happy to talk about them after the talk. To conclude, we have seen three sets of puzzling findings. and a two-system model that we think can account for all these findings, as well as making novel predictions that we can test. In this model, initial object representations in the PR system are very sparse. These object representations become more detailed as events form event categories and identify causally relevant features for predicting outcomes in each category. Infants' core knowledge guides their interpretations of information that's included in your object representation. A key strength of infants' approach to learning about the physical world in this way is fast learning. EBL is very efficient because it relies on analytical as well as empirical evidence to identify new features. Another key strength is powerful generalization within categories. Once a feature is identified as relevant for an event category, it is used for reasoning about any events in the category and any pertinent facets of the events. In contrast, though, one sharp limitation of this approach to learning about the physical world is that there is no generalization across categories. Infants learn separately about each event category, which can lead to striking discrepancies in the responses to similar events from different categories. And finally, speaking very broadly, what we've seen today, I hope, is that infants' representations of objects in physical events are system-specific. The same object may be represented slightly differently in the object file and physical reasoning systems. And they're also event-specific. Even within the same physical reasoning system, the same object may be represented differently in different event categories. I'd like to again thank you for all listening. And I just realized that this is much shorter than what I had anticipated. But we can open up for questions, and then we have time, I can show you the other predictions that I had.
Thank you, Yi, for the presentation. Are there any questions from the audience? If there's no questions, then I guess that we can finalize the session then. Okay, so let's thank Yi for her very nice presentation, and
thank you, everyone.
okay.
Thank you.